Preface. Welcome to University Physics, an OpenStax resource. This textbook was written to increase student access to high-quality learning materials, maintaining highest standards of academic rigor at little to no cost. About OpenStax. OpenStax is a nonprofit based at Rice University, and it's our mission to improve student access to education. Our first openly licensed college textbook was published in 2012, and our library has since scaled to over 25 books used by hundreds of thousands of students across the globe. OpenStax Tutor, our low-cost personalized learning tool, is being used in college courses throughout the country. The OpenStax mission is made possible through the generous support of philanthropic foundations. Through these partnerships and with the help of additional low-cost resources from our OpenStax partners, OpenStax is breaking down the most common barriers to learning and empowering students and instructors to succeed. About OpenStax's resources. Customization. University Physics is licensed under a Creative Commons Attribution 4.0 International (CC BY) license, which means that you can distribute, remix, and build upon the content, as long as you provide attribution to OpenStax and its content contributors. Because our books are openly licensed, you are free to use the entire book or pick and choose the sections that are most relevant to the needs of your course. Feel free to remix the content by assigning your students certain chapters and sections in your syllabus in the order that you prefer. You can even provide a direct link in your syllabus to the sections in the web view of your book. Instructors also have the option of creating a customized version of their OpenStax book. The custom version can be made available to students in low-cost print or digital form through their campus bookstore. Visit your book page on openstax.org for more information. Errata. All OpenStax textbooks undergo a rigorous review process. However, like any professional-grade textbook, errors sometimes occur. Since our books are web-based, we can make updates periodically when deemed pedagogically necessary. If you have a correction to suggest, submit it through the link on your book page on openstax.org. Subject matter experts review all errata suggestions. OpenStax is committed to remaining transparent about all updates, so you will also find a list of past errata changes on your book page on openstax.org. Format. You can access this textbook for free in WebView or PDF through openstax.org, and for a low cost in print. About University Physics. University Physics is designed for the 2 or 3 semester calculus-based physics course. The text has been developed to meet the scope and sequence of most university physics courses and provides a foundation for a career in mathematics, science, or engineering. The book provides an important opportunity for students to learn the core concepts of physics and understand how those concepts apply to their lives and to the world around them. Due to the comprehensive nature of the material, we are offering the book in 3 volumes for flexibility and efficiency. Coverage and scope. Our University Physics textbook adheres to the scope and sequence of most 2 and 3 semester physics courses nationwide. We have worked to make physics interesting and accessible to students while maintaining the mathematical rigor inherent in the subject. With this objective in mind, the content of this textbook has been developed and arranged to provide a logical progression from fundamental to more advanced concepts, building upon what students have already learned and emphasizing connections between topics and between theory and applications. The goal of each section is to enable students not just to recognize concepts, but to work with them in ways that will be useful in later courses and future careers. The organization and pedagogical features were developed and vetted with feedback from science educators dedicated to the project. Volume 1. Unit 1. Mechanics. Chapter 1. Units and measurement. Chapter 2. Vectors. Chapter 3. Motion along a straight line. Chapter 4. Motion in 2 and 3 dimensions. Chapter 5. Newton's laws of motion. Chapter 6. Applications of Newton's laws. Chapter 7. Work and kinetic energy. Chapter 8. Potential energy and conservation of energy. Chapter 9. Linear momentum and collisions. Chapter 10. Fixed axis rotation. Chapter 11. Angular momentum. Chapter 12. Static equilibrium and elasticity. Chapter 13. Gravitation. Chapter 14. Fluid mechanics. Unit 2. Waves and acoustics. Chapter 15. Oscillations. Chapter 16. Waves. Chapter 17. Sound. Volume 2. Unit 1. Thermodynamics. Chapter 1. Temperature and heat. Chapter 2. The kinetic theory of gases. Chapter 3. The first law of thermodynamics. Chapter 4. The second law of thermodynamics. Unit 2. Electricity and magnetism. Chapter 5. Electric charges and fields. Chapter 6. Gauss's law. Chapter 7. Electric potential. Chapter 8. Capacitance. Chapter 9. Current and resistance. Chapter 10. Direct current circuits. Chapter 11. Magnetic forces and fields. Chapter 12. Sources of magnetic fields. Chapter 13. Electromagnetic induction. Chapter 14. Inductance. Chapter 15. Alternating current circuits. Chapter 16. Electromagnetic waves. Volume 3. Unit 1. Optics. Chapter 1. The nature of light. Chapter 2. Geometric optics and image formation. Chapter 3. Interference. Chapter 4. Diffraction. Unit 2. Modern physics. Chapter 5. Relativity. Chapter 6. Photons and matter waves. Chapter 7. Quantum mechanics. Chapter 8. Atomic structure. Chapter 9. Condensed matter physics. Chapter 10. Nuclear physics. Chapter 11. Particle physics and cosmology. Pedagogical foundation. Throughout university physics you will find derivations of concepts that present classical ideas and techniques, as well as modern applications and methods. Most chapters start with observations or experiments that place the material in a context of physical experience. Presentations and explanations rely on years of classroom experience on the part of longtime physics professors, striving for a balance of clarity and rigor that has proven successful with their students. Throughout the text, links enable students to review earlier material and then return to the present discussion, reinforcing connections between topics. Key historical figures and experiments are discussed in the main text, rather than in boxes or sidebars, maintaining a focus on the development of physical intuition. Key ideas, definitions, and equations are highlighted in the text and listed in summary form at the end of each chapter. Examples and chapter opening images often include contemporary applications from daily life or modern science and engineering that students can relate to, from smartphones to the internet to GPS devices. Assessments that reinforce key concepts. In chapter examples generally follow a three-part format of strategy, solution, and significance to emphasize how to approach a problem, how to work with the equations, and how to check and generalize the result. Examples are often followed by check your understanding questions and answers to help reinforce for students the important ideas of the examples. Problem-solving strategies in each chapter break down methods of approaching various types of problems into steps students can follow for guidance. The book also includes exercises at the end of each chapter so students can practice what they've learned. 1. Conceptual questions do not require calculation but test student learning of the key concepts. 2. Problems categorized by section test student problem-solving skills and the ability to apply ideas to practical situations. 3. Additional problems apply knowledge across the chapter, forcing students to identify what concepts and equations are appropriate for solving given problems. Randomly located throughout the problems are unreasonable results exercises that ask students to evaluate the answer to a problem and explain why it is not reasonable and what assumptions made might not be correct. 4. Challenge problems extend text ideas to interesting but difficult situations. Answers for selected exercises are available in an answer key at the end of the book. Additional resources. Student and instructor resources. We've compiled additional resources for both students and instructors, including getting started guides, PowerPoint slides, and answer and solution guides for instructors and students. Instructor resources require a verified instructor account, which you can apply for when you log in or create your account on OpenStax.org. Take advantage of these resources to supplement your OpenStax book. Community hubs. OpenStax partners with the Institute for the Study of Knowledge Management in Education, ISKME, to offer community hubs on OER Commons, a platform for instructors to share community-created resources that support OpenStax books, free of charge. Through our community hubs, instructors can upload their own materials or download resources to use in their own courses, including additional ancillaries, teaching material, multimedia, and relevant course content. We encourage instructors to join the hubs for the subjects most relevant to your teaching and research as an opportunity both to enrich your courses and to engage with other faculty. To reach the community hubs, visit www.ourcommons.org/hubs/OpenStax https://www.oercommons.org/hubs/OpenStax. Partner resources. OpenStax partners are our allies in the mission to make high-quality learning materials affordable and accessible to students and instructors everywhere. Their tools integrate seamlessly with our OpenStax titles at a low cost. To access the partner resources for your text, visit your book page on openstax.org. About the authors. Senior contributing authors. Samuel J. Ling, Truman State University. Dr. Samuel Ling has taught introductory and advanced physics for over 25 years at Truman State University, where he is currently professor of physics and the department chair. Dr. Ling has 2 PhDs from Boston University, one in chemistry and the other in physics, and he was a research fellow at the Indian Institute of Science, Bangalore, before joining Truman. Dr. Ling is also an author of a first course in Vibrations and Waves, published by Oxford University Press. Dr. Ling has considerable experience with research in physics education and has published research on collaborative learning methods in physics teaching. He was awarded a Truman Fellow and a Jepson Fellow in recognition of his innovative teaching methods. Dr. Ling's research publications have spanned cosmology, solid-state physics, and nonlinear optics. Jeff Sani, Loyola Marymount University. Dr. Jeff Sani earned a B.S. in physics from Harvey Mudd College in 1974 and a Ph.D. in solid-state physics from the University of California, Los Angeles in 1980. He joined the faculty at Loyola Marymount University in the fall of 1980. During his tenure, he has served as department chair as well as associate dean. Dr. Sani enjoys teaching introductory physics in particular. He is also passionate about providing students with research experience and has directed an active undergraduate student research group in space physics for many years. William Mobes, formerly of Loyola Marymount University. Dr. William Mobes earned a B.S. and Ph.D., 1959 and 1965, from the University of Michigan. He then joined their staff as a research associate for 1 year, where he continued his doctoral research in particle physics. In 1966, he accepted an appointment to the Physics Department of Indiana Purdue Fort Wayne, IPFW, where he served as department chair from 1971 to 1979. In 1979, he moved to Loyola Marymount University, LMU, where he served as chair of the Physics Department from 1979 to 1986. He retired from LMU in 2000. He has published research in particle physics, chemical kinetics, cell division, atomic physics, and physics teaching. Contributing authors. Stephen D. Drugger, Alice Kolakowska, University of Memphis. David Anderson, Albion College. Daniel Bowman, Ferrum College. Deidre Demery, Georgetown University. E.D.W. S. Ginsberg, University of Massachusetts. Joseph Trout, Richard Stockton College. Kevin Wheelock, Bellevue College. David Smith, University of the Virgin Islands. Takashi Sato, Kwantlen Polytechnic University. Gerald Friedman, Santa Fe Community College. Lev Gasparov, University of North Florida. Lee LaRue, Paris Junior College. Mark Lattery, University of Wisconsin. Richard Ludlow, Daniel Webster College. Patrick Model, Indiana University Kokomo. Dao Peng, University of Nevada, Las Vegas. Kenneth Podolak, Plattsburgh State University. Reviewers. Salame Ahmad, Rochester Institute of Technology, Dubai. John Aiken, University of Colorado Boulder. Raymond Benge, Tarrant County College. Gavin Buxton, Robert Morris University. Eric Christensen, South Florida State College. Clifton Clark, Fort Hays State University. Nelson Coates, California Maritime Academy. Hervé Collin, Kapiolani Community College. Carl Covado, Arizona State University. Alejandro Kazani, Imperial Valley College. Danielle Dallafave, the College of New Jersey. Nicholas Darnton, Georgia Institute of Technology. Ethan Deneau, University of Tampa. Kenneth Denisco, Harrisburg Area Community College. Robert Edmonds, Tarrant County College. William Falls, Erie Community College. Stanley Forrester, Broward College. Umesh Garg, University of Notre Dame. Maurizio Gianodi, Berry University. Brian Gibbs, Dallas County Community College. Lynn Gillette, Pima Community College West Campus. Mark Giroux, East Tennessee State University. Matthew Griffiths, University of New Haven. Alfonso Hinojosa, University of Texas Arlington. Stuart Jensen, Alma College. David Kagan, University of Massachusetts. Sergei Katsev, University of Minnesota Duluth. Jill Leggett, Florida State College Jacksonville. Alfredo Loro, University of Calgary. James McLaren, Tulane University. Pon Maheswaranathan, Winthrop University. Seth Major, Hamilton College. Oleg Maximov, Excelsior College. Aristides Marcano, Delaware State University. James McDonald, University of Hartford. Ralph McGrew, SUNY Broome Community College. Paul Miller, West Virginia University. Tamar Moore, University of Portland. Farzaneh Najmabadi, University of Phoenix. Richard Olenek, the University of Dallas. Christopher Porter, Ohio State University. Liza Puji, Manukau Institute of Technology. Baishali Ray, Young Harris University. Andrew Robinson, Carleton University. Aruvana Roy, Young Harris University. Gajendra Tulsian, Daytona State College. Adria Updike, Roger Williams University. Clark Vangilder, Central Arizona University. Stephen Wolf, Texas State University. Alexander Worm, Western New England University. Lei Zhang, Winston-Salem State University. Ulrich Zerker, Cleveland State University.